All right, so welcome everyone, and thank you for joining us. So today it's our pleasure to have Ali Seraj, who is actually visiting and sitting right next door. So it's our pleasure to have him around. And he will tell us about the exciting topic of multiple charges in gravity. Please.
Thank you very much. Hello, everyone. Good afternoon. Let me thank organizers, and in particular Mark and Tara, for the invitation and the opportunity to talk here. In a free world, I would have talked about gravitational memory effects, in which I have done some recent work, and I'm quite excited about it. But the organizers asked me to talk about this topic. So there we go, multiple charges in gravity. I should mention that several years ago, I worked out this multiple charges in Maxwell theory as the charges associated to some natural symmetries in harmonic gauge. And then we extended that to the case of gravity with Geoffrey Compere and Roberto Oliveri. But then, so this is actually the first half of the talk, which I explain these concepts. But then there was this exciting recent works about higher spin charges and W1 plus infinity algebras and so on by Stromger, and then some nice work by Laurent Friedel and collaborators. So we were inspired by that, and we have found that, in fact, there is a close relationship between our multiple charges and these higher spin charges. And this will be the second half of my talk. Let me start. Yeah. So I usually have a lot of motivations, but here with this audience, I guess I can quickly jump into the discussion. Just one motivation slide, which is that multiple expansion is a powerful tool to describe fields in various physical situations. For example, in Maxwell theory, if the fields are stationary, the electric and magnetic fields can be described in terms of two scalars, which are harmonic functions and are given by these expressions, standard expressions. So the nice thing about these expressions is that, as you see, the radial dependence of the fields is kind of locked to the angular dependence. And these coefficients here are called the electric and magnetic source multiple moments. So this is a useful expansion of the field because, as you see, if the observer is at large distance, the higher multiple modes decay very fast, and therefore the first few terms in the sum provide a good approximation of the result. Now, if you have radiation, this totally destroys this structure, and already at leading order in 1/r, where you have the radiation, you will have all the multiple moments. Now these coefficients are called radiative multiple moments, which multiply these vector spherical harmonics. But still, the multiple expansion provides a good approximation of the result, because you can show that in a non-relative v over c is much smaller than 1, where v is the typical velocity of the source. You can show that these radiative multiple moments scale like v over c to the power L. And therefore, in a non-relativistic regime, you can truncate this sum to the first few multiples. And this is actually the basis for the post-Newtonian theory in gravity. Now, this was a quick introduction of multiple moments. What I did in the past was that I showed that these multiple moments are related to some charges, some symmetries in Maxwell theory. And now let me explain that. So if you take harmonic gauge, which is given by this equation, the residual symmetries of this gauge is given by solutions to the wave equation. Now we can fix the gauge further by imposing that the zeroth component of the gauge field is 0. And therefore you find that the residual symmetries are now time-independent harmonic functions, whose solution can be expanded in harmonics like this. So you see that we have two branches of solutions, one growing in R and one decaying in R. The second branch is like pure gauge, and therefore we find that the large gauge symmetries in harmonic gauge, which are called multipole symmetries, is given by this set. As you know, we can define charges using Noether theorem or Hamiltonian methods associated to these large gauge symmetries, which is given by surface integrals of the electric, the normal component of the electric field smeared by the gauge parameter. You can also define dual charges by replacing the electric field by magnetic field. And this will be this is not another charge in the usual description of the theory, but if you go to a dual formulation of the theory, then these are the natural motor charges. And if you have a duality invariant formulation of the theory, you will have both charges at the same time. Now you can now you can compute the charges corresponding to these multiple symmetries, and these are the definition. So QLM is the charge of this lambda ln, which is r to the L by ln. Now let's compute these charges. So in a stationary configuration, when you compute these charges, you find that they are given by these expressions. So you see that the charges reproduce the source multiple moments up to some numerical coefficient. So this is interesting because it promotes the multiple moments to some charges associated to some symmetries in the theory. So the usual definition of this source multiple moments is given by volume integrals over the source, but our charges are given by surface integrals. So the structure of these charges is that you have some overleading symmetries. So you remember that these multiple symmetries grow with R. There is R to the L, which diverges at large R. But this overleading behavior captures some subleading information in the field configuration. And this is why we get finite result for the charge. But I should stress that because of this overleading behavior, these symmetries are not allowed to act on the phase space because they are restricted by the boundary conditions. If you impose some boundary condition on the gauge field. So the constraint surface somehow intersects each orbit of these multiple symmetries at single points. But still you see that as I showed here, the charge associated to these symmetries is finite on the constraint surface, at least for stationary spacetimes. Now let's talk about gravitational multiple moments. So before I start, I just
Can I ask a question about that?
Yes. Yes, please.
Can you explain that more? I mean, there's two questions. One is maybe that you explain a bit more what you just said. The other one is that if you really take the general, you know, the overleading vector field and you apply and you compute a Noether charge, in fact, you will find this finite contribution, but you also will find a sum of divergent contribution, right?
Exactly.
So to extract this charge, you have to do a renormalization
True.
Is that what you're saying here, that they are not on the orbit?
No, here, yeah, yeah. Um,
Or Mimi, okay. So about the
yeah,
first
I'll
one.
come back to that point,
Okay.
divergences later. But here, yes, I'm just saying that if you demand that you want, for example, your gauge field to go like 1/r, then you are not allowed to act with these overleading symmetries on the gauge field because it produces some R to the L component in the gauge field, which is not allowed by the boundary conditions.
Okay, but it's related to the first thing, is that maybe what, okay, the fact that maybe what's well defined is the renormalized charge definition.
Right. Yeah, that's yeah. I think I will come back to that. I don't have a an answer to this question, but I'll come back to this later. Okay, so yeah, I discussed these things a bit more detailed in the gravitational case, which is more interesting. So I just want to start with the fact that there is an alternative to spherical harmonics, which is called symmetric trace-free harmonics, or STF harmonics. So this is actually a useful alternative because for practical reasons, it's very, for computational things, it's very useful. So in Cartesian coordinates, you have this normalized vector ni, which is the ratio of xi over r. And then you can introduce this multi-index notation n capital L, by which I mean the multiplication of L such vectors ni. And now if you can consider this contraction FL and L, where FL is some tensor with L indices. And now this is really the Einstein convention for summing over all the indices. So it turns out that if this tensor FL is trace-free over each two indices, then this quantity FL and L is actually an eigenfunction of the Laplace operator. So this quantity FLNL, where FL is trace-free, is on the same footing as YLN. As you see, the eigenvalues are the same. So you can use these SDF tensors to expand scalars, vectors, tensors, and so on. Okay, so with this comment, now gravitational multiple moments are defined. So the point is that up to coordinate transformations, the gravitational metric in Einstein gravity is described by two sets of multiple moments called the mass and spin moments, MLM and SLM, or in the STF notation, M capital L and S capital L. So this means that you have L indices here. Now, the way that these are defined are different, but Thorne defined the multiple moments in his seminal paper in the 80s by through the components of the metric in a very specific gauge, which is called the canonical harmonic gauge. So this is a refinement of the harmonic gauge. However, if the spacetime is a stationary, there is a more geometric and gauge invariant way to define the multiple moments, and this was done by Gerock and later by Gerock and Hansen. And the idea here is that you have the Killing vector, the time-like Killing vector psi, from which you can define its norm and its twist this way. And it turns out that the norm encodes the mass multiple moments, while the twist encodes the spin multiple moments. And finally, when you compute these multiple moments for the Kerr black hole with parameters M and A, you find that the multiple moments are given by these simple expressions. This is actually very important because by gravitational wave detections, we can, in principle, not now, but maybe in the near future, extract the first multiple moments of the source by looking at the ring down phase of the gravitational wave. And then from there, we can compare the result with these expressions and see if they match with these constraints or not. And this is a test of the uniqueness theorems in general relativity. Okay, now, so this is about gravitational multiple moments. Now, the way that we found gravitational multiple moments in this paper was to derive them from some Noether charges associated to some multiple symmetries. So the way that it works is that you again go to the harmonic gauge, which is given by this, where this ugly G mu nu is called the Gothic metric perturbation. And then again, residual diffeomorphisms are solutions to the wave equation. You can again fix the gauge further by demanding the 0, 0 and 0i components of the metric behave in this specific way. And as a result, you find that the generators of the multiple symmetries are given by these three sets of vector fields. And so the first one looks a bit like, so you see that all these vectors depend on one scalar function epsilon, which is time independent and it solves the Laplace equation. So it's a harmonic function. The first vector looks like somehow a generalized boost vector. You see this explicit t dependence here. The second one is kind of rotational vector. And the last one is kind of a translation vector. So to have a more clear understanding of these vectors, you can expand this epsilon, which is a harmonic function in spherical harmonics. And we clearly see that the Poincaré generators are in the first two harmonics of this set. So for example, L equals 0 in this generator K gives the time translation, L equal 1 is boost. Rotations are L equal 1 of this J, and the spatial translations are L equal 1 of this P. And then all the higher L we call the mass, spin, and momentum multiple symmetries. So we see that this provides an infinite extension of the Poincaré algebra, but note that this set doesn't is not an algebra under Lie bracket because the commutator of two harmonic vectors is not a harmonic vector anymore. But you may be able to define a modified bracket which closes this algebra. For example, when the space has some finite boundary, you can show that although the commutator of two harmonic vectors is not a harmonic vector, but it differs from a harmonic vector by some pure gauge, by which I mean a vector that vanishes at the boundary. So this way you can define a modified bracket which closes the algebra. The case where the boundary is asymptotic is more involved because you have divergences and so on. Okay. Now let's talk about the charges associated to these multiple symmetries.
Sorry, Ali. So
yes.
What is the bottom line? Is that you don't know what are the structure constants of this algebra?
We have not worked out this for the case of asymptotic boundary like flat space with asymptotic boundary. But using this, I think I can work it out, but I don't remember the result at the moment. Yeah, but yeah, this is a good point. Yeah.
Okay, because at some point you're going to talk about matching the symmetry algebra between this one and W infinity, right?
Yeah, yeah.
You need to understand.
True. Yeah, yeah.
Okay.
Okay. Yeah. Again, I'm not sure if I will address that question completely, but yeah, let's see. Okay, so now about the charges. So we use the Varnish brand expression for the charge, and for the metric, we following Thorne, we use the metric written in the canonical harmonic. Sorry, do you?
Yeah, we lost your screen. Is this?
I don't know what happened. I share the screen again. Do you see it?
Yeah, yeah, it's back.
Okay. Okay, so now if you compute the charges for the mass multiple symmetries, we see that they reproduce exactly the mass multiple moments up to some numeric factor, and the charge corresponding to spin multiple symmetries reproduces the spin multiple moments. So again, this result promotes these canonical multiple moments to some charges associated to multiple symmetries. Okay, so now this is about what Laurent mentioned. So when we have radiation, so far I was talking about stationary configurations where the charges are finite and well defined, but as soon as we introduce radiation in the system, this destroys the structures and introduces some divergences in the charges. As you see here, the charge in linearized gravity, when you have radiation, the charge is a sum, you have a polynomial in powers of R. So when the boundary is at large R, these results blow up.
So Ali, I have a question about the previous one because you went fast. Why is the P charge vanishing? It's because you're talking about static?
No, no, because so I started with harmonic gauge, but you can fix the gauge further by somehow, for example, if I go to the center of mass, I kill the total dipole
Yeah, but
charge.
we know it's not a gauge fixing, it's a symmetry fixing, which is very different, right?
Well, yeah.
cannot
I
do
mean,
that. It's just,
true.
right?
Yeah, true. Yeah. I mean, we just followed Thorne to
Yeah,
compute
but
the charge in this specific gauge, but maybe in a more general setting, we can relax this condition and have finite values for the momentum charges.
you would have, because otherwise the algebra, it breaks the symmetry algebra.
True. Yeah.
Okay,
I mean, the reason that we did that was that we just wanted to reproduce these two sets of multiple moments, which are somehow accepted by the community to describe the gravitational field. But of course,
then
there
there should be a third set. So physically, what does this third set of momentas mean?
these are somehow the gauge part. Of course, it's not the gauge in the sense
No,
of
it's not gauge. It should be the position of the black hole. Actually,
true.
I mean, and it's
Exactly
it has physical information.
true. I totally agree. Yes.
Okay. Yeah, because in the past people confuse gauge with symmetry.
Yeah.
That's part
Yeah,
of this.
true. It's a symmetry. Yeah. I agree. I mean, the fact that we have two sets of multiple moments is related to the fact that the gravitational field has two polarizations. So, but there are additional information about, as you said, about the location of the source and so on, which are somehow encoded in this third set. But yeah, just for practical reasons, we fixed this one. Okay, so going back to the radiation case, we see that these are divergent. And at the moment, the only thing that we could say about this result was that if we take the finite part of these results, which means that we take n equals 0 in this, sorry, this p should be n. Look at this first one. So if you take the n equals 0, this is a finite piece. And we see, so this time derivative is killed because n equals 0. And then we see that the finite part of this result reproduces again these canonical multiple moments. But then recently, inspired by these recent works about higher spin charges and so on, we realized that one should think of these coefficients in this polynomial as somehow independent physical quantities. So yeah, so let me define these coefficients as Q n Lm. So n refers to the number of derivatives here, and Lm are the labels of the harmonics. So we have Q plus, which corresponds to this one, Q minus, which corresponds to that one. And moreover, one can show that in a non-radiative spacetime, these quantities, Q plus minus, are conserved, are time independent, and therefore it's somehow legitimate to call them charges. And now the claim is that these quantities are closely related to the higher spin charges that has been introduced in this great paper of Laurent Friedel and collaborators. Okay, so in the next part of the talk,
sorry, Ali, a quick question. Can you said that you got these charges using the Varnish-Brand formula?
Yes.
And can you remind us which prescription you chose for the integrable part? Because you're considering radiative case right now.
Well, yeah, here was about the stationary spacetime. For the non-stationary, for the radiative part, well, this is the linearized gravity, so I don't know.
So if it's linear gravity, you're basically just using the expression of Thorne. No need to invoke Varnish-Brand, really.
What do you mean by Thorne?
Thorne, you're using those expansion. How do you, maybe just how are you defining these multiple charges in the radiative case?
So this is the chart, the Varnish-Brand charge. So this is for a linearized perturbation H. Okay.
So what is little k then? Because usually this charge is given as an, with the non-integrable formula, and then you have to select the integrable piece. So that's why
at linearized order there is no integrability issue, because integrability is when you want to integrate over.
So you're ignoring the flux basically. I just want to understand, when you said Varnish-Brand, for me, it's this big formula, which is equivalent more or less to the standard calculation of xi of omega, right? So it doesn't give you the delta of something a priori. Just wanted to understand what is, well, maybe you can just tell me what is this little k? What is the definition of little k?
This is some, as you said, is a long expression involving eta, the Minkowski metric, and the metric perturbation H. So it differs from the Ayerwald expression by some but by one term, which is 0 for killing vectors. But
so maybe you want to say, this is the infinitesimal charge.
Exactly, this is the infinitesimal.
So this is not Q. This is okay. This is infinitesimal charge. So you're not worried about whether you can integrate it or not. You're just going to talk about it.
Because I'm a linearized theory, so I consider a perturbation, which is an infinitesimal. In the case of a stationary case, you can this integrability issues are relevant, but then you can show that somehow at the end they work well. I mean, I cannot say it.
Okay, fine. Thank you.
But maybe we can discuss about it.
Thank you.
Yeah. Okay. So so in the second part of the talk, I'll talk about the relation between these quantities and the higher spin charges and so on. Okay, so to do that, I need to go to the Bondi gauge, which you know very well. It consists of retarded time, radius, and angles on the sphere, and it's defined by these gauge fixing conditions, in which the metric takes this general form. And then we have an additional condition on the determinant of this spherical component of the metric. And interestingly, this determinant condition specifies the form of this GAB here to be of this form, where gamma AB is the unit round metric on the sphere, and this calligraphic CAB is a symmetric trace-free tensor on the sphere. You see that the trace part is completely fixed by this trace-free part. This was pointed out in this recent paper, nice paper by Grant and Nichols.
Do you take gamma to be the fixed round sphere metric here, or gamma can also be?
Yes, I take it to be the fixed metric on the sphere.
Okay.
Well, yeah, I take it to be time independent, but it can be some given metric on the sphere. Well, yeah, the Ricci scalar of this is 2, for example.
So it's fixed to 2.
Yeah.
It doesn't matter for the result you want to say, right? It can be any.
Yeah, perhaps it doesn't matter. Yes.
It doesn't. Yeah. Okay.
Yeah. I mean, if you want to have super rotations and so on, you need to relax. Anyway. So okay. Now, if you perform an asymptotic expansion of these quantities that appear in the metric and impose that the spacetime is asymptotically flat in this sense, we see that, for example, this calligraphic CAB contains at leading order the usual Bondi shear, and then there is no 1/r term, and then at more subleading orders we have these terms which I call EAB and n running from 2 to infinity. And then we have the mass aspect and angular momentum aspect appearing in the expansion of these other quantities in the metric. The important thing about these three quantities is that they obey some evolution equations, which I also call a balance equation. So the structure of these equations is that, for example, for the mass aspect, you have the time derivative of the mass aspect is given by this expression. So it involves a linear term in this NAB and a quadratic term in NAB, where NAB is the News tensor, which is the time derivative of the shear. And it has the crucial feature that it vanishes for non-radiative spacetimes. There is a similar equation for the angular momentum aspect, which I have not written for the reason that it will become clear in a moment. And the reason is that there is an ambiguity in the definition of these quantities. For example, here for the NA, if I shift NA by some quantity XA, then the right-hand side will be shifted by the time derivative of XA. So somehow I need a prescription to fix this ambiguity. And for example, for the angular momentum aspect, I use this ambiguity to define this calligraphic NA, which is given by this expression. And then from there, I define the generalized BMS charges, which is defined as the an integral over the sphere of the mass aspect multiplied by the supertranslation function, and this improved angular momentum aspect multiplied by an arbitrary vector on the sphere. And now with this improved quantities, the balance equations, the Einstein equations, take this form. So as you see, the structure is as follows. We have a term linear in the news on the left, and then we have the flux term, which is this quadratic in the news and vanishes when the news is 0. And then we have the time derivative of these aspects. The fact that we use this calligraphic NA is supported by various arguments. First of all, it's supported by the soft theorems in the sense that from soft theorems you get exactly this term for the soft flux, the flux of soft gravitons. Also, if you compute the charges, the charge for the angular momentum from this calligraphic NA, you see that it matches with the Ashtekar-Struble charge derived based on symplectic methods and so on. And finally, it's shown recently by Watt and his student that it's only this prescription of the charge that is smooth under small deformations of the integration surface. So this is an important point. So if you use other prescriptions, if you deform the integration surface by a small amount, then the charge suddenly blows up and so on. Okay.
Sorry, I have a question about that because, you know, with Daniele and to get the soft theorem, we have a unique prescription for what we call the renormalized charge, and it comes from the covariant charge renormalized to have the right property at infinity. There's really no wiggle room there. So are you working with—
Are you referring to this last property?
No, I'm referring to the paper with Daniele, which is gravity from symmetry, where we identify, and the paper with Anna, where we define this renormalized charge to be, you know, we proved that we have all the soft theorems coming from the charge.
Yeah, I think this calligraph NA matches with your choice.
Yeah, so it's the covariant charge.
Covariant, I should add this property also here, which is the covariance under DFS2, superpositions.
Yeah, that's how we kind of identify them. It's really the covariance property that just selects uniquely these.
This is a crucial point. Yeah.
But it's the psi1 of the Weil tensor, right? This covariant momentum.
Well, then there's the renormalization. So
but this one NA. But so this NA here, is it the psi1 of the Weil tensor or the renormalized psi1 of the Weil tensor?
If you go back to the formula, maybe Ali, if you can see it's renormalized. There's a U dependence.
Okay, yes.
Right. So if you forget the U, it's the psi1, and then the U dependence is the renormalization.
Okay. Thanks.
Right. But I mean,
yeah, I totally agree that this covariance is
very solid now. There's no ambiguity. You just ask for what is the symmetric object, and you get a unique answer.
We were, I totally agree with that, but we were somehow, motivated by somehow this pattern that appears here for the soft part. I will come back to this in a second, but yeah, that this covariance is a very robust argument. I agree. So if I integrate over these balance equations over time, I find, and if I keep in mind the definition of Mellin transform of a function, which is given by this. So you have the function of u multiplied by u to the power s. Typically, this is defined as s minus 1, but here it turns out that it's more natural to take it to be s. Well, it's just a convention. And then integrate over time from 0 to infinity. So I assume that my new tensor is vanishing before some initial time, which I take it to u equals 0. And now if I take an integral over time of the balance equation, I find these equations for the Mellin transform of the news of rank 0 and 1. So here, I mean, I'm referring to this S, which is 0 here and 1 here. So this is very interesting. And now recall that there are other balance equations for each EAB n that I defined before as the expansion of this calligraphic CAB in the spherical part of the metric. These equations were worked out in this paper of Grant and Nichols. And one may wonder if those equations provide or constrain the higher modes in the Mellin transform of the news. And this is what I want to address now. So if you fix the ambiguity in a proper way, you find that the whole list of balance equations take this form. So the first two are just the ones that I showed before for the mass and angular momentum aspect. And these other equations are for the EAB 2 up to, and for general N actually. Here, calligraphic EAB is an improved version of EAB that appeared in the metric. And well, the details are not important, but the structure is as follows. So you have the news tensor multiplied by u to the power n. And then you have some spherical operators, derivatives acting on the news. And on the right-hand side, you have the flux, which is vanishing when the news is 0. And then you have the time derivative of your aspect at order n. So now, as you clearly see, if I integrate over time of this equation, I get an equation for the nth Mellin transform of the news. So altogether, I have a set of equations for all integer Mellin transforms of the news. And this is, I guess, interesting. Now, inspired by previous discussions, it's very natural to define charges for all these list of aspects. So this is my list. I mean, this is my extended I don't know BMS charge. So the first two lines are actually the first line. This is the super translation charge. This is the dual super translation charge. The second line, the first one is the super angular momentum charge. The other one, which is its dual, is the center of mass charge. I mean, super center of mass charge. And then this third line is the so-called, I call it higher spin charges. I've not yet proved anything, but I just call it higher spin charges.
But they are the same that we introduced with Anna and Daniele, right? That's exactly what we did.
Yeah. Yes. Okay. Yeah. Okay. Yeah. Well, these EABs. Is it exactly what you have? Well, if you accept that these are the same thing, I'm very happy, but I was not sure. anyway, yeah, these are the whole list of higher spin charges. And of course, this parameter of the charge phi is a function on the sphere, so we can expand it in multiple moments, and thereby we define these charges q plus minus n lm, or in the STF notation, q plus minus n comma l. Okay, and the point is that these quantities we claim that are related to the quantities that I showed to you before in the computation of the multiple charge. Yeah, the coefficients of the divergent powers of R. So let's go back to the balance equations. So the balance equations take this general form. So we have, well, integrated over time. So we have delta Q and LM, where delta is actually the difference between this charge at early and late times. And then we have the soft flux, or the memory term, and then we have the hard flux. So there are two situations that might appear. The general case is that this memory term is non-vanishing. And therefore, the way that you should read this equation is that it specifies the memory in terms of the change in the charge and the hard flux. So in other words, the memory or the soft part is specified by the hard process. But there are special cases where this memory term vanishes for some reason. And the reason is that, as you remember, I had these spherical operators that was acting on the News tensor in the linear term. And those spherical operators kills some certain harmonic modes, LM. And for these modes, there is no memory, and therefore the equation looks like this. So this is really a strict constraint over the hard dynamics. And in other words, it's a radiation reaction equation. So if you have, if you know the radiation, you can infer from that the changes in the source of the radiation. And this is in principle useful for the gravitational wave analysis and so on. So the picture that you should have in mind is that in the generic case, you have the system, for example, a binary system. Its initial conditions, initial state is specified by Q in. Its final state is given by Q out, and you also have the flux of radiation. And these quantities specified the soft radiation, the low frequency part of the radiation, which is not directly observable, perhaps. But in this specific case where the memory is zero, just knowing the flux specifies the change in the system, which is characterized by this delta Q. Okay, so now let me talk about these special modes. I call it memoryless modes. In particular, for n equals 0 and 1, and they include the Poincare charges. So the Poincare charges have no like memory. And then, but this is not all. For n greater than 2, well, for n equal 2, there is no such mode. But for L equal 3, you can show that L equal 2 modes are in this set. And you can show that actually these charges are the Newman-Penrose charges that was defined in the 60s. And this is actually proved by Godasgar and brothers and Pope in 2018. But actually, there are actually more charges like that. For n larger than 3, you can show that all L less than n minus less than n are like memoryless, and then these I would call generalized Newman-Penrose charges. Yeah, as I said, these charges are in principle important for gravitational wave analysis because they provide some radiation reaction equations for you. Okay, now finally, let me talk about, let me compute these charges in non-radiative spacetimes. So, the picture that I want you to have in mind is that I have like a sandwich spacetime, which is something like this. So you have initially before some initial time, the spacetime is non-radiative. Then you have radiation, and after some time, again you go back to a non-radiative configuration. I can call this non-radiative spacetime as a radiative vacuum. This is the terminology of Strominger. And the point is that the initial and final vacua differ from each other. So the radiation leads to a vacuum transition. And the question is to provide a complete characterization of these radiative vacua. So several years ago, Strominger labeled the vacua by supertranslation field, but now we know, and I will show you that actually the gravitational vacuum is much more degenerate than the one I mentioned, and it's actually characterized completely by this set of higher spin charges. So this is what I show next. And to show that, I use this result that we obtained 2 years ago with Blanchet and collaborators, that the multiple expansion of the shear is given by this form, where U, L, these two quantities U and V, are the so-called radiative multiple moments, which are given at linear order by the L time derivative of the canonical multiple moments, ML and here SL. So if the spacetime is non-radiative, which means that the news is 0, it means that the L+1 time derivative of the canonical multiple moments are 0. And this implies that a non-radiative spacetime or a radiative vacuum is specified by these functions, which are polynomials in different powers of U, and the coefficients are called MLK and SLK. So these two quantities completely characterize a non-radiative spacetime or a vacuum, where K here is between 0 and L. Okay, now I show that actually these quantities are nothing but these higher spin charges. So let's see how that works. So to compute the higher spin charges in the linear theory, I need an expression for all these data in the metric. And again, this was done in my paper with Blanchet and others, Roberto, Guillaume Fay, and Geoffrey Compere. Yeah, these quantities are given in terms of multiple moments in this way at linear order. And now you can compute the charges, the higher spin charges, and you find that in non-radiative spacetimes, they reproduce this QNL reproduces up to numeric factors exactly those quantities that parameterize a radiative vacuum. Well, this is for L larger than N. For L less than N, the charges are 0 at linear order. This set corresponds to the the generalized Newman-Penrose charges, which turn out to be zero in the linear theory, but if you consider nonlinear interactions into account, then perhaps they are non-zero. And this is something that we want to compute later. But what we see here is that a radiative vacuum is uniquely characterized by these higher spin charges, Q plus minus NL. Just a brief comment about the relation between these charges and the ones that Laurent introduced in his paper, because maybe it's obvious for him, but it was not so clear to me. But so anyway, they showed that the higher spin charges reproduce this W1 plus infinity algebra. And from my understanding, if I take the parameter of the charges to be a spin weight, the spherical harmonic of weight n, spin n, and harmonic Lm, then these charges, this charge that they define reproduces our charges here. So this we have checked for n equals 0 and 1, and we are now in the middle of the computation of generic n. So let me not talk about that more here. I'm sorry. So let me finish the talk by this summary. So there are different things to study later. In particular, I would like to compute these generalized Newman-Penrose charges at quadratic order. I find it this will be very interesting. But there is one comment, and see if there are applications or implications for binary systems. But something that I want to stress here, and unfortunately I don't have time to spend more on this, is that you remember that I assumed like sandwich spacetimes where the News tensor decays exponentially at large time in the future and past. And this is what also Laurent assumes in his paper, and also other people make this kind of assumption. But there is an important point here, is that it's very well defined in the linearized theory, but as soon as you consider nonlinear effects, there is this so-called gravitational tail effect, which destroys this behavior. So you can show that if you consider tail effects. And so let me tell you what is a tail effect. It's the fact that, so you have some source which has some total mass m, which somehow curves the spacetime around it. And now you have, and now this source emits gravitons, which have to propagate in this curved spacetime. And at any point in this potential, well, they can scatter back. And therefore you have gravitons that, for example, if you are very far from the source on the right, you have gravitons that propagate to the left for a large amount, and then scatter back and go to the right. So it's because of this fact that you keep receiving gravitons all the way up to u to infinity. Although the source might not be radiating anymore, but you still keep receiving this gravitational waves. And you can show that these tail effects, I mean, expanded at large u, take this form. So you see that there are every power of every negative power of u from n equal 1 to infinity. And now these this behavior leads to actually simple poles in the Mellin transform of the news at integer values. And this is very funny because these integer values are exactly the points where we have computed those flux balance equations. So exactly at the point of those flux balance equations, you have divergence. So all of your equations are divergent. So this requires that we need to redefine or reinterpret those equations. And this is something important to study. And I believe that these are related to the so-called quasi-normal modes in the gravitational wave radiation, because if you look at the literature in black hole perturbation theory, for example, the Regge-Wheeler equation and so on, you see that the quasi-normal modes of the black hole corresponds to simple poles in the Laplace transform of the wave. And I think this is very closely related to that. Yeah, thank you very much for your attention.
Thanks a lot, Ali. Okay, we have time for some more questions. Yeah, Laurent.
I already asked questions, so if there's somebody else. Okay, I have a question about that last remark. That's very interesting. So can you say more? Quasi-normal modes are poles in.
Sorry, your voice is.
Sorry, we lost your...
sorry. Yeah, sorry. I have a question about the last point you made, which sounds very interesting. These quasi-normal modes are poles of the Mellon transform. What is the location of these poles? We not expect them to be exactly integer value, right? Positive integer.
Yes. Well, this quasi-normal modes discussion. So it's sometimes done in the Fourier transform of the wave. Sometimes a more rigorous study uses the Laplace transform, and then the location of the poles is related to the frequencies of the quasi-normal modes. But here, what I'm saying is that given this behavior of the tail effect, and this we know again from our analysis of tail effects in the paper with Luc Blanchet, we see that there are terms proportional to u to the minus n with every integer power of n, including 1. And if you make a Laplace transform of the news, actually, so take a time derivative and then take the Laplace transform, the Mellin transform, you see that there are poles at every integer value n. And this is the points where we computed those balance equations. I'm saying that, yeah, and we know that there are divergences in those equations when we have we don't have this exponential decay assumption. So yeah, I'm saying that we have to somehow, I have the impression that one needs to compute the residues of those equations, not the exact numerical values of those equations. Somehow one should equate the residues. I've not thought about it this much, but
okay. But the quasi-normal modes are poles, but they are not along the real axis, right? They're in the complex plane.
Right. Yes. Yeah.
Now I have a question about the tail effect. So the tail effect requires that you're in the background, like the background ADM mass is non-zero, right?
Yes. True.
Okay. So somehow this tail effect doesn't apply to the calculation of the S matrix, where the memories are.
Yeah, if you don't have because
in the S matrix you start from gravitational vacua to gravitational vacua. There's no background black hole there.
Well, as soon as you have ADM mass, I think this effect appears. So I don't know if the ADM mass is 0 in that context? Because anyway, you have total energy, and maybe still you will have.
I think it might be different. It's scattering in it would be interesting, but it's a different. It's scattering in a vacua instead of scattering in a background.
Yeah, I mean, if you have massive particles, for sure you have this Bell effect, but maybe for massless scattering, this doesn't exist. I'm not sure about that.
And then the remark about what you were saying, why is it obvious to me that this is the same, is because in the paper with Anna and Daniele, this is exactly what we did. We said there's a unique notion of charges aspect for a given spin, the normalized one, and then the soft component of that charge is the residue, is the soft charge, which is the residue of the Malan transform at integer n. So that's the thing, and this is how we could get all the soft theorems in that setting. So the equations we wrote are and the way we got the algebra is by integrating this equation and computing the bracket on the radiative phase space. So that part of your talk is
true.
Kind of,
okay. Yeah. Okay. Very nice. Yes.
Maybe also, if you look at that paper, there's a subtlety in the sense of the charges. When you look at this radiation component, as you're saying, there's kind of two types of multipolar charges. There's the Newman-Penrose charges, and then there's the local charges, right? The radiation is kind of, or the charges splits into, there's the global charges and the local charges, as you're saying. The global charges don't have a soft component.
Okay, in that sense.
And the local charges. So the one for which we really verify the algebra is the local part of the charges. And okay. I would expect that the global one also satisfies some kind of global version of W infinity, but this one, it's not known at this stage.
I see. Right? Interesting.
So yeah, if you look, we in the linearized case, you can clearly see how this, this charge is split.
I see. Okay, very, very interesting.
I mean, I think the split is the same one as you were referring to, the Memoryless and the other ones.
I understand. Yeah. Okay, perfect. Yes, thanks.
I have a question, curiosity, and maybe it's related to these last things Laurent and Daniele just pointed out. But since you are seeing these Newman-Penrose charges among the subleading ones, did you get some intuitions from the formulas as to why they would be conserved also in the radiative case? Some geometric or physical intuition?
For the radiative case, they are not time independent. I mean, they're not conserved in the sense of time independent, but they satisfy this kind of equation.
But they should be, aren't they? Well, if we're talking about the same Newman-Penrose charges, they should be absolutely conserved even in the radiative case, right? Meaning that they don't depend on the retarded time. That's what I always thought. But you're saying they are not?
No, but Newman-Penrose proved the conservation for the linear version. But
No, the non-linear ones. No, the linear ones, it's clear what they mean. But it's the non-linear ones that they're absolutely conserved and it's unclear what they mean.
Not for the IO spin 4, 5, 6, etc. There's something about spin 3 which seems
okay.
Yeah, I'm only talking about the 10 Newman-Penrose ones.
It's true.
This one, the spin
right.
3. The spin
yes.
3.
Did you have some intuition as to why they're absolutely conserved?
Okay, this is a good point, because maybe for some reason this this flux term vanishes for L equal 2.
Okay.
It's possible, but I didn't know that. So yeah, I will look at the expression. Yeah, okay. I didn't know that there. This is
this is a bizarre result in some sense that nobody has really kind of dig into, right? So this spin 3 charge is supposed to be the mass times the spin, minus the quadrupole square, and supposed to be conserved. But I don't think anybody has used that in gravity wave formations and stuff like that.
Okay. So you say that this takes the form of like the mass times the spin minus.
It's the mass times angular momentum minus quadrupole square.
Okay. Where is that derived or discussed?
It's in Newman-Penrose.
Ah, Newman-Penrose. Okay.
68 no sé si.
I'm too young. Sorry.
Yeah, but I think there's a lot of questions about it in the subsequent literature, and nobody has really found a proper way to understand that. It seems very surprising to have an extra charge conservation there.
Okay.
And I don't think they are conserved in the presence of matter too. It's just pure gravity.
Right. Yeah. This is all pure gravity.
Yeah. But to go back to maybe the question of Simone, there is something about this distinction between the symmetry, which are memoryless, which are global symmetry, right, like Poincaré, and the one which are associated with the soft theorems. That is, they constrain the gravitational theories through Ward identities, and conceptually, I don't know, they kind of the global symmetric one should have an effect on usual field theory, right? Whereas the memoryless should be, okay, they're purely gravitational. So
yes,
understanding what they mean is
right.
But also maybe because of some people of the audience here, I know Henning is around, you know, I mean, in some sense, there seems to be this kind of infinite sets of charge and symmetry acting on gravity. So going back to the question of Simone, what does that mean? You know, if you have an infinite set of conserved charge, conserved at I0, not along sky, then, you know, it seems that there's a form of integrability pointing his nose, but
maybe they just describe the infinitely many ways observers can look at the same solution. Infinitely many inequivalent inertial observers.
No, because as Ali showed, no, these are just the expansion of the radiation field, when, you know, the expansion of the metric field when you go inside. So if you have all of them, in fact, there's an older result by in the Living Review that they said that if you have all of these charges, you know, and then you can reconstruct the bulk component of the metric and the radiation field.
Yeah, that would be amazing, for sure. Absolutely.
Yes. Well, maybe I can make a comment here. So these equations, as I said, specify the integer values of the Mellin transform of the news, but to reconstruct the news, so I mean the inverse Mellin transform is an integral over imaginary line, so you don't need only these integer values, but all, I mean, all the real. And so I'm not sure if this provides enough information to reconstruct the news, or maybe I'm confused. Somehow, for me, this gives the non-oscillatory in some sense part of the news, or yeah.
Well, let's say it should be put as a question. You know, it's an infinite data that determines an important part of the news tensor. The question is how much?
How much can we reconstruct? Yeah. True.
Maybe all of it, half of it. Yeah.
Yes. Okay. True. Exactly. And sorry, just I forgot to mention some point, which is that Geoffrey Compere had the main and major contribution in all this this second part of the talk. So yeah, I should give the proper credit to Geoffrey.
All right. So if there are no further questions, we can thank Ali again.
Thank you.
Thanks.
Thank you.